Okay, so in this video we're going to start section 4.2, which is about traveling waves. And so we're done with our 4.1 section about, simple harmonic motion and basic oscillations. So like I said, 4.2 is about traveling waves, which, as the name implies, are waves that travel, as opposed to standing waves, which we'll talk about in section 4.5. Now, most waves that we think of when we think of waves, whether they're electromagnetic or sound or water waves, etc., are traveling waves that move through space. And again, we'll talk more about standing waves, which is a different type of phenomena in section 4.5 in the next unit. So just to kind of go quickly through what 4.2 entails. Okay, so this is just some of the basic preliminary information about traveling waves. Okay, that you can read through yourself. Notice it says a common characteristic of all traveling waves is that they carry energy, but generally the medium through which they travel will not be permanently disturbed. Okay, now when we talk about medium, that's basically the substance through which a wave travels. We'll talk more about that later. But usually when we talk about a wave moving, it's energy that is moving, not necessarily matter. Okay, and we'll talk about that later in this video. Okay, some of the things in 4.2 that you need to know about. Obviously, we'll talk about traveling waves. This 4.2, we'll be talking kind of a lot about basic information and characteristics of traveling waves. Wavelength, frequency, period, wave speed, all of those are pretty simple ideas. We'll talk about the difference between transverse and longitudinal waves. We'll talk about the nature of electromagnetic waves and the nature of sound waves. Okay, and then as far as what you must be able to do, remember the applications and skills for each section tell you what the IB expects you to be able to do. You must be able to explain the motion of particles of a medium when a wave passes through it for both transverse and longitudinal cases. Sketch and interpret displacement distance graphs and displacement time graphs for transverse and longitudinal waves. Take a look at that later. Solving problems involving wave speed, frequency, and wavelength. That's a very easy thing to do. There's nothing complicated about that at all. And then investigating the speed of sound experimentally. Okay, now when we talk about the electromagnetic spectrum in the next unit, you should be aware that according to the IB, students should be aware of the order of magnitude of the wavelengths of radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. Okay, and so when we get to talking about the EM spectrum, I'll briefly mention that, but the IB does expect you to roughly know the order of magnitude of those wavelengths. If nothing else, to be able to put the different parts of the EM spectrum in order from shortest to longest wavelength. But we'll talk about that as it comes up. And of course, electromagnetic waves are used extensively for national and international communication, whether you're talking about things like Wi-Fi, radio, television, communication between different countries through satellites, and so on. Okay, so a traveling wave, again, is obviously a wave which travels from one location to another. And I've got a little video clip that I want you to take a look at. But I said this before, in general, a wave can transmit energy but not matter from one location to another. Okay, and so when you think of something moving in a wave, what's actually moving from point A to point B is energy, not matter. Okay, so I will link that video so you can check that out. These are just some examples of traveling waves. Okay, so just to kind of lead into this, consider a taut rope, so a rope that's been pull tight, which is anchored securely to a table. Okay, now if you take your hand and you grab one end of the rope and you move it up and down, you can send a single wave pulse through the rope that looks something like this. Okay, so the wave pulse goes and it hits the end, and that's a single wave pulse. Now you can keep on moving your hand and produce what's called a continuous traveling wave. And as you think of this example, notice that the rope itself is not moving to the right. If you think about what the individual rope particles are doing, each rope particle is just vibrating up and down locally in place. So in other words, if you were to just pick a point on this rope and follow it along, that point on the rope is not moving to the right, it's just moving up and down. Okay, so that's what I said when I said before that traveling waves carry energy, not matter. Let's see that one more time. Okay, so what you're seeing is not the rope itself moving to the right, but you're just seeing each individual particle on the rope moving up and down. Kind of like that. And I could do this with a spring as well. I could attach a spring to a wall. I could grab one end and I could move my hand back and forth. Okay, I could do a single wave pulse, or I could keep doing it. And this is also a type of wave because there's also transfer of energy. Now, it might not be a wave that you're familiar with, but that is in fact a type of wave. And again, the spring as a whole doesn't move to the right, but the spring particles, or the parts of the spring, just move left and right locally. Okay, so that's what we mean when we say that waves carry energy and not matter. Okay, now generally speaking, you can classify waves into one of two categories. You have mechanical waves, which by definition require a medium to travel through. And again, when I say medium, I mean the substance through which the wave travels. So for example, when you talk about sound waves traveling through the air, the medium in that situation would be the air. All right. When you talk about water waves traveling through the water, the medium in that situation would be the water. Okay, and so when I talk about a wave medium, I'm just talking about what is that wave traveling through. Now, most waves require some type of medium to travel through. Electromagnetic waves are the only type of wave which do not require a medium. They can travel through a medium. There's absolutely nothing wrong with electromagnetic waves traveling through a medium, but they do not require a medium. Okay, they can travel through what's called a vacuum. So the only waves capable, for example, of traveling through outer space are electromagnetic waves, because those don't require a medium to travel through. Now, electromagnetic waves we'll talk more about later, but there's a whole spectrum of electromagnetic waves. Everything from infrared light, visible light, ultraviolet light, microwaves, radio waves, microwaves, gamma rays, X-rays, all of those are examples of electromagnetic waves. We'll talk more about those in detail later. Okay, so we've got mechanical waves and we've got electromagnetic waves. Okay, but there's also another way to classify waves. Okay, you can classify waves based off of what the particles that make up the wave are doing. Okay, and so definitions are important, so make sure you're adding this down to your notes. But the two types of waves we're going to focus on are transverse waves and longitudinal waves. Okay, now in a transverse wave, the wave travels perpendicular to, that means at a right angle to, the directions that the particles making up the wave are oscillating. And in a longitudinal wave, the wave travels parallel to the direction that the particles are oscillating. Okay, so I'm going to link two videos here so that you can see the difference between transverse and longitudinal waves in action. Okay. However, I do want you to think back to the example that we saw a minute ago of the string attached to the wall. In the case of the string attached to the wall, when we move our hand up and down, the particles making up the string also go up and down. And so in that example, the wave traveled to the right. Okay, that's the way that the wave pulse on the string went, but the actual particles making up the string were going up and down. And so that was an example of a transverse wave. Now, when most people think of a wave, they are thinking of a transverse wave. If I were to ask you, draw me a wave, you would probably draw me a picture of a transverse wave, because that's the most common type of wave, and most waves are transverse waves, which is why that's probably the type of wave that people are most familiar with. Okay, but you also have a longitudinal wave, in which the wave travels parallel to the direction that the particles making up the wave are oscillating. Okay, so for example, if you think back to the spring attached to the wall, that was an example of a longitudinal wave because the hand holding the left end of the spring was moving left and right, and the particles in the spring itself were moving left and right, even as the wave was traveling to the right towards the wall. Okay, so you have transverse waves and you have longitudinal waves. And I will tell you right now that most waves are transverse waves. By far the most common example of a longitudinal wave that you'll see is a sound wave. Okay, besides sound waves, it's not super common to see longitudinal waves and problems. Again, most waves are transverse waves. All right. Okay, and that's what I said before. So examples of transverse waves, all electromagnetic waves are transverse waves. A crowd wave, so if you ever go to a sporting event or NASCAR or something and the crowd does the wave where they stand up and everybody shouts and whatever, and doing the wave, people know what that is. That is an example of a transverse wave because as you watch it happen, it looks like there's a wave traveling across the stadium, but each individual person in the wave is standing up and down. Okay, and up and down would be perpendicular to the direction of the wave motion, and so that would be a transverse wave. Waves on a string are transverse waves as well. Everything from jump ropes to wave on a guitar string, violin string, any type of string instrument. Again, most waves are transverse waves, and this is what a transverse wave would look like. You see the wave traveling one direction and the particles making up the wave traveling perpendicular to that direction. Okay, now the other type of wave is a longitudinal wave. Now, I said before that by far the most common example of a longitudinal wave is a sound wave. Sound waves are longitudinal waves. In fact, as you talk and you're talking to somebody, your voice, the air coming out of your mouth, pushes on the air molecules and makes them go back and forth parallel to the direction that the wave is traveling in. And then those air particles, collide with air particles nearby, and through that mechanism, eventually sound kind of travels out and other people can hear you. You can also produce longitudinal waves on a spring like we saw. That's what I mean by slinky waves. And this is kind of what a longitudinal wave would look like. Notice in this case that the wave is moving to the right, and the particles making up the wave, in this case the particles of the spring, are oscillating left and right, parallel to the direction of the wave motion. Okay, now let's talk about the different parts of waves. I would recommend that you sketch these pictures into your notes and take these down in your notes. I think for the most part, all of these things are pretty basic pieces of information. It's all pretty self-explanatory, and you can figure things out from the diagram. Okay, transverse waves have crests and troughs. Longitudinal waves don't have crests and troughs. They have compressions, and they have rarefactions. Okay, the place where the particles kind of bunch up together, that's called a compression. Okay, that is equivalent to a crest on a transverse wave. And then the places where the particles spread out the most, that's called a rarefaction. Not to be confused with refraction, which is something completely different. Now, both types of waves have what's called wavelength. And wavelength is basically, it's a length, it's got length in the name, but it's basically the distance that the wave travels before ending up in the same equivalent location. And so there's lots of different ways to measure wavelength. Typically what you'll hear people say is, you measure from crest to crest, okay, the distance from crest to crest. But you could also measure from trough to trough. You could also pick any point at random on a wave and keep measuring the distance until you get to that same equivalent point. Okay, and so it doesn't have to be crest to crest necessarily. And it doesn't just have to be for a transverse wave. Okay, so for a longitudinal wave, the area between two compressions, that is one wavelength, or the distance between two rarefactions, that is also one wavelength. So it's the distance between one point on a wave and then the next point on the wave where the wave repeats itself. Okay, now the symbol for wavelength, which you might know or maybe not, but the symbol for wavelength is the Greek letter lambda. Okay, so lambda, that's this upside down Y looking thing. That is the symbol for wavelength. That is very typically measured in units of length, obviously. So everything from meters, millimeters, centimeters, etc. I do want to point out that you need to be very careful when you're doing calculations involving wavelength. You need to be very aware of the units that wavelength is being measured in. Okay, the SI unit would be meters, of course, but it's very common to see wavelength in other units. Okay, could even be nanometers if you're talking about, visible light. All right, so let's go to the next slide. Okay, so we talked about transverse waves and longitudinal waves already. This is just showing you the difference between crests and troughs, compressions, refractions. Okay, so if you didn't get that in your notes before, make sure you get that down. All right, so moving on, categorize a water wave as transverse or longitudinal. Well, if you've ever been fishing and you used a bobber, then you probably saw the bobber moving up and down. Okay, and the reason for that is waterways are transverse waves. Okay, the wave moves one way. The particles making up the wave, in this case the water particles, are moving up and down perpendicular to the direction of wave motion. Okay, so you should be very familiar with the definition of these types of waves because definitions are important. Okay, you don't want to be missing definition questions if you're asked those questions. Okay, we also talked about sound waves, how sound waves are a very common example of longitudinal waves. Okay, so for example, if you have a speaker, the speaker is vibrating, pushing on those air particles, and as the cone pushes outward, it squishes the air molecules together and causes a spot of compression. Okay, and then as it goes out into the air molecules, spread out, and that's called a refraction. And so if you were to just, think of these little dots here as the individual air particles, this is basically what you would see. Okay, so this is a very simplistic model of a sound wave. And notice you can see in some places the dots come close together, that's a compression, and some places they spread apart, that's a rarefaction. Okay, so okay, we'll talk more about wavefront and rays later on. So actually, I don't want to spend too much time talking about wavefronts and rays now because we'll talk about that later. Okay, now imagine you have, some type of transverse wave, and imagine you think of each of the particles making up that wave as one of these blue dots. Okay, and so what we've done here is we've taken each of these blue dots and we've placed each one in simple harmonic motion, and each particle has a slight phase difference compared to the particle next to it. Okay, and so what you get is this, and this is just a transverse wave. So each of these blue particles has the exact same frequency and period as a particle next to it, but there's a slight offset. Okay, there's a slight phase difference. And so you can think of for a transverse or longitudinal wave, you can think of the individual particles making up the wave, each of those particles being in simple harmonic motion. And of course, we know what simple harmonic motion is, and we know what kind of behavior that follows. It's like a sinusoidal type of thing. Okay, and so that's one reason we learned about simple harmonic motion first. All right. Okay, now we've talked about wavelength before. Okay, that should not be new. Remember that's given by the symbol, the Greek letter lambda. We've also talked about period before. Period for wave is the time it takes a wave crest to travel exactly one wavelength. Okay, so imagine a wave traveling, through space. In one period, the distance that's traveled is one wavelength. Okay, so you can think of period as the time for one particle to complete one full oscillation, but equivalently, you can also think of it as, the in that amount of time, the wave travels through one wavelength. Okay, and period is given the symbol capital T. Okay, now we have this quantity which we call wave speed. And this is very simple. I mean, wave speed is exactly what it sounds like. It's basically how fast the wave is moving, okay, through a given medium. Now, because by definition, in one period, the distance a wave can travel is one wavelength, there is a very simple relationship between the wave speed, the wavelength, and the period. And that is just this. V equals lambda over t. Okay, now, it looks a little fancy maybe, but at the end of the day, this is basically your old distance over time equation, right? Lambda is the distance traveled. The time is one period, okay? And so that's basically how wave speed is defined. Okay, V equals lambda over t. Now, frequency, we've talked before about how frequency relates back to period, but frequency is, in the context of waves, how many wave crests pass a given point per second, and the unit for frequency is hertz, Hz for hertz. And because of the way frequency is defined, frequency is 1 divided by the period. And so if you take, frequency is 1 divided by the period and you substitute it in for the period in this equation, you get this equation, which I will write right here. Okay, so V equals lambda over t. If you rewrite this as lambda times 1 over t, then you get lambda times f. Okay, and so this is the most commonly seen form of this equation. This is what is called the wave equation. The wave speed is equal to the wavelength times the frequency of that wave. Now, for reasons which I don't really understand, this is not how this equation is written in the data booklet. In the data booklet, this equation is written as C equals lambda times F, which I really don't like because C is the speed of light in a vacuum, which is the speed of an electromagnetic wave, and so this equation of course applies for an electromagnetic wave, but really the more general equation is this one up here, okay, because this is for any old wave. If you're talking about an electromagnetic wave and the speed just happens to be c, then you could put in c there. Okay, so this is what you'll see in the data booklet, but this is really how you need to think about the wave equation. Okay, V equals lambda times F. There's usually not anything super complicated about using this equation, as long as you know it. Okay, the only thing to watch out for is the units on things, because frequency, when you talk about frequency in hertz, that's technically cycles per second. And so you do need to pay attention to the units on the wavelength and the wave speed. But besides that, this equation is very simple to use. Okay. Okay, so just a few simple examples. A hand is moved in simple harmonic motion. A spring is moved in simple harmonic motion by the hand as shown. The hand moves through one complete cycle in 0.25 seconds, and metric ruler is placed beside the waveform. Okay, so we can actually see the different parts of the wave. Now, what type of wave is this? Well, this is obviously a longitudinal wave. We can see the areas of compression and refraction. And remember, the way you measure wavelength is you pick one point on a wave. It doesn't matter which point. But you pick that point and then you measure the distance to the next equivalent point. Okay, so in this case, they measure from the right side of a compression to the right side of the next compression, and they find that to be 4.7 centimeters. Now, of course, there's some type of uncertainty in there, but you cannot worry about that on this example. Notice that they convert the wavelength to from centimeters to meters. You may or may not have to do that depending on what the question is asking you to calculate. The period, it says that the hand moves through one complete cycle in 0.25 seconds, and so that is the period. Okay, remember, period is just the time it takes for one complete oscillation. And so the wave speed would be the wavelength divided by the period. And so that's a very easy calculation to do, 0.19 meters per second. Okay, if you wanted to write the wave speed in terms of centimeters per second, that would be fine. Just make sure that you're being very careful with your units. So, for example, you could have done 4.7 divided by 0.25, and then that would have given you, 19. But then your units would have been centimeters per second instead of meters per second. Generally speaking, as long as your units are correct, the IB is fine with whatever, but do read the question carefully, because sometimes they do specify what units your answer should be in. Okay, so we're going to do some examples with this in the next video. For now, I want you to add this down to your notes. The two types of traveling wave graphs that you need to be familiar with are displacement distance graphs, which are typically labeled, y and x, and displacement time graphs. And it's really important that you understand the difference between these two graphs. Okay, a displacement time graph is basically showing you a snapshot of the wave at a single moment in time. Okay, so if you imagine like a wave, let's say, somebody is shaking a rope up and down and there's a wave. If you were to take a picture of that wave frozen in time and then place that on a graph, that would be a displacement distance graph, okay, at a single instance in time. What you can do with that graph is you can measure the distance from one point on the wave to the next equivalent point, and that distance will be the wavelength. Alright, so you can use a displacement distance graph to find the wavelength. A displacement time graph, on the other hand, rather than show you the whole wave at a single point in time, it basically focuses on a single point and how that single point changes over time. Okay, and then what you can do with a displacement time graph is you can use a displacement time graph to measure the period, because when you're thinking in terms of time, the time for one complete oscillation of each of those points is the definition of period. And so make sure that you know what type of graph you're looking at. Make sure you understand how to use both of these graphs. We'll do some examples of this in the next video. But the last thing I want to say is when you are looking at these two types of traveling wave graphs, pay close attention to the units on both axes, okay, because it's very common in topic 4 to give you graphs where, maybe displacement is measured in centimeters, millimeters, maybe seconds, instead of measured in seconds, maybe it's in milliseconds, or maybe it's in, 10 to the minus 6 seconds, or something like that. Okay, so really what we're doing in this unit is not super complicated, but one of the more common ways to get messed up is based off of units. Do make sure that you pay close attention to the units. So in the next video, we will do some examples with these traveling wave graphs. As always, please let me know if you have any questions, and I'll see you guys in the next video.